All right, my name is Ed Armstrong, and today we're going to talk about parallel design. Particularly, the topic is going to be model and paradigms. However, that's actually a fairly small topic in parallel design, so we're going to cover a number of other things. I'm going to slightly go through the outline of designing a parallel program, which is going to involve metrics and ways of judging and reporting performance. If you're to write a paper or proposal, what people who are in the field would be looking for. I'm also going to build up a bit of a vocabulary to start you with parallel programming that will help you, particularly regarding other seminars that we offer. We'll show basic design patterns. Now, that's the title, and it's also going to be at the end of the seminar. And the goal of that is to show you what kind of things you would keep in mind while programming a parallel program. They're not necessarily rules, and anybody who's familiar with sequential design patterns will realize that there are things that you have to keep in mind and not necessarily follow to the key. Because the whole idea behind design patterns is so that you can communicate to other programmers as well as to your future self on what you're doing on a macro scale. And that's hopefully what we're going to do today, is give you something, an ability to communicate to other programmers what is going on with a parallel program. So that being said, this is not necessarily solely for people who are going to go out and program something using one of a variety of languages, but rather someone who might be talking to a programmer or getting specs or giving a proposal for resources, or possibly even just using a package and understanding maybe what the package is talking about. So that being said, also, we are not going to do any language level demonstrations. Any code that I have, or very little that I have, is going to be pseudocode to kind of show you what's going on. So this does not necessarily require that you be a programmer to understand what's going on. All right, so the first kind of level we're going to talk about is what kind of parallelism we're getting. So there's implicit and explicit parallelism. Implicit is the stuff that you, as a programmer, say is going to happen. It is by way of a, that's explicit. Implicit is by way of language design, or which the compiler will take care of, and you don't necessarily say or specify what parallelism you want, or what kind of structures you want. This has the benefit in that you don't have to worry about the communication or the task division or really anything to do with designing how the parallelism works. However, in all likelihood, you're going to get less than optimal code. The stuff you do by hand is often going to be better than the stuff that's generated. It's also much harder to debug in that you don't know what's going on. The more you know what's going on, the easier something is to debug. Now, explicit is the stuff by way of deliberate language constructs or annotation on top of existing languages that you will put into code that will tell it how to parallelize it. For example, if you use a pthreads library in C, or if you use MPI or something where you are putting in specific code into your program, then we're talking about this. Now, it's potentially very efficient code because you're going to hand tune it. However, you have now introduced a number of bugs. These are the kind of bugs that are going to happen while coding that are unique to parallelism, which we'll cover today. And it's also a much longer development time. Designing these parallel programs, you either have to start from scratch, or you have to bring over an otherwise sequential program and introduce parallelism into it. So we are going to be particularly talking about explicit parallelism today, because implicit parallelism will come with a package, such as R or something that has it built in. The terms are interchangeable, but for all my examples, we'll be talking about explicit parallelism. There's also a number of types of parallelism. This is kind of the levels of parallelism you'll get. There's hardware and software parallelism. There's parallelism from your chip right up to your user interface. It's all using some form of parallelism. On the hardware level, you're going to get start with instruction level parallelism, and it's what allows the chip to basically perform instructions much faster than I guess they did before they introduced it. But we're not really going to get into that. Slightly above that, we're going to talk about thread level parallelism. And this is something the user can do. Shared memory, cache, message passing, even though message passing is almost at a cluster level. And then now there's no defining line here. When I say thread level, I mean typically you're talking about your on-chip communication or shared memory. When you're talking cluster level, then you're talking between chips. And it's kind of a level of parallelism that you're going to get. Now, in a different set of language, a different nomenclature, is software. Now, software and hardware is not necessarily, one does not exclude the other, but we're going to be talking about stuff like task parallelism. And this is more the way that you're going to divide up how you program. Data parallelism, also how you're going to divide up the data which is going into the program in order to optimize your parallelism. And of course, hybrid task data, which is what most of your programs are really going to do. You're going to have some form of task parallelism and some sort of data parallelism. When talking, there's a formal description of types of parallelism. It's known as the Flynn taxonomy. And this is a way of dividing up or describing what kind of parallelism you have. Now you'll see it's a 2x2 grid here, and that you have single instruction and multiple instructions, single data, multiple data. When we say single instruction, that means you're performing the same instruction across usually your architecture. If you're saying multiple instructions, it's going to be a different instruction depending on where the data is. Single data, it's going to perform the instructions on the same piece of data. Multiple data, it's going to either perform the same instruction or multiple instructions on different pieces of data. To kind of give you an idea of what these different ones represent, so we'll say SISD, single instruction, single data. That's a sequential. That's not even parallel. That's your typical everyday sequential model. When we're looking at single instruction, multiple data, you're going to be thinking about your standard GPU model. So what's going on there? You've got single instruction. You've got many microcores spread across your GPU. You're going to give them all one instruction and then feed data through it. Change the instruction, feed data through it. So it's going to be different data points, usually traditionally 3D locations that you want to transform. More modernly, we're using GPU programming languages to grasp this or to take advantage of this multi-microcore architecture. Fairly new compared to some of the other ones. Well, multiple data, multiple instruction, multiple data. This is your common multi-core model in that you have a number of cores with their own instructions and their own data, and you just control how the flow works. Multiple instructions, single data, not really commonly found in practice, but if you're aware that it exists, there are some obscure examples, usually not necessarily implemented, that you'll find. But what we're going to focus on today, not really the standard single core CPU, but more the parallels. So we're going to look specifically at SIMD, single instruction, multiple data, and MIMD, multiple instruction, multiple data. And we're not even going to look at that. These are what we're regarding in regards to the rest of the seminar. Now, our target hardware, and your target hardware in general, is what's known as a cluster computing. While there are a number of other parallel models or hardware models, this is the one you are most likely to take advantage of or to be introduced to, particularly as a new user. The more experienced users will feel free to use other ones. But so the cluster computing, what's going on with the cluster? A cluster is made of a number of nodes. So each node, usually in some case, or with some communication between them, which could be Ethernet, usually higher speed than Ethernet, but depending on where you are. And each node, which usually consists of some sort of motherboard, specialized motherboard for these types of things, but they can be, in the case of a Beowulf cluster, commodity hardware, the same kind of motherboard you'd find in your desktop. And these are just linked together. Now what you'll want is in these motherboards, usually more than one CPU, but can be one, which then on that CPU, down to the low, again, a level lower is the multi-core architecture. And then each core will have their own level of cache, a shared cache, and so on and so forth. And what I'm trying to get at here is you have to keep in mind while writing your program at which level you're writing it for. If you're only communicating here on a multi-core CPU, it's going to have less considerations about communication than if you're going to go across the CPUs, which again will have less communication lag or slowdown when you go across a node. And then where are the nodes located? Are the nodes located in the same rack, or are the nodes located in physically different locations? And that's going to have more. And all of these things will increase or decrease some of the considerations that have to take place when programming. So the first model, and this is symmetric multiprocessor, which you'll often also hear called a shared memory model. And what this means is typically applied to something that will all share some sort of memory. Typically homogeneous, sometimes heterogeneous, which means homogeneous meaning you're going to have different access times between the CPUs to the main memory. The heterogeneous. The homogeneous means that the access times are going to be relatively the same. There's no reason, no physical reason that they should be different. Now, if we take a look here, so what's going on is we've got different levels of memory, in that we have a main memory, a cache, and then an onboard cache. And they all communicate, well, not the caches communicate with each other across a bus, which also communicates with the I/O, the input-output. Now, this is a simplified model. They can get a bit more complex than this with different buses. But this basic model is here to show you that when you're doing communication, when you do your thread, this is typically threaded programming, you'll hear it called. So you'll instantiate a thread, which will be put onto a process. You don't really have control which CPU the thread goes on, but they'll be divided up. And you have to concern yourself with stuff like what's on the cache locality. Because you're all using the same shared memory, the shared memory can also be reflected at the same time in the cache. That means that if you have access, say, variable A in this CPU here, it will have pulled it from main memory. If this CPU then wants to access variable A, it also has to pull it from main memory. The problem is now, if the second CPU alters A and the first CPU goes to use it, it's now known to be dirty, which means it has to go back and do a refresh. And things like this will slow down symmetric multiprocessing. Other things that will usually slow it down is you'll notice that the memory still uses the same bus as the I/O. Doing a lot of I/O, input-output, just willy-nilly throughout your program is going to cause problems when accessing memory, particularly if more than one thread wants to access the I/O at the same time. So you'll notice a bit later on when we talk about the actual models, this is a big consideration, is when the communication between the CPUs takes place and when the communication with the input-output takes place. And this is one of the major things that will slow down your program. So some of the things about SMP, shared memory systems. So you're going to have a global address space. You're all going to use the same main memory. This is the same thing you're used to in sequential programs. You can almost think about it the same way. However, you have the locality issue. So synchronizing it can be a bit of a tricky concept to grasp. Data sharing is fast and is also consistent in uniform memory access systems. In the non-uniform or the heterogeneous systems, it may be different. That means that you may have a CPU that's attached differently. I do believe most, if not all, of our clusters are UMA. If you use something, I think the PlayStation 2, back when they were using that for high-performance computing, had a NUMA architecture. Anyways, that's just a side note. Another thing is memory consistency model, cache coherence. You have to worry about whether or not the memory is consistent, what kind of changes, how that's going to slow you down. because each process, as opposed to the message passing, which we'll get to in a moment, each process will be possibly sharing a bit of memory. Now, I say it lacks scalability, in that you have to wait for hardware advances to get more cores, you have to wait for hardware advances to get more onboard cache, and so on and so forth. What this means is the more CPUs you put on, the more you're taxing that bus. And you yourself can't really just keep adding, because eventually it gets prohibitively expensive, or you just hit a limit. These are where the engineers have to come in and fix it. So when you are worried about a bit more scaling, we're going to talk about, so for message passing interface, this is more the model that we're going to use on the cluster level when you're talking about between node communication. This does not mean it's excluded from the SMP or the core level. You can do message passing on the core level if you like, or on the CPU level. It's just it's more appropriate if you're using it between nodes. And what we're talking about here then is we're talking about a distributed memory model. We are no longer sharing the main memory between processes. Each one will have its own unique main memory. So they're not mapped. And this saves you a lot of trouble with cache coherency and locality, etc. However, with no globally accessible memory, you now have to use some sort of process to communicate. The most common one is MPI. You use sockets on your own if you want to roll your own. But you're going to be using something to communicate between processes. When this, of course, implies more overhead, more time. Note that there are hybrid systems, and that you can use both threads and message passing in the same system. They're not mutually exclusive. It's just a division in programming models. The memory is local and scalable. There's no need for local memory synchronization. What I mean by scalable is if you add another cluster, you're typically going to, or another node, you're typically going to add more memory. Makes it a lot more scalable than when we were talking about the shared memory, or when you add another CPU, it's all going, you're not really adding more memory per se. You may require specialized data structures. That means you may not use the same with the SMP programming. You're going to be doing a lot of programming that is familiar from your sequential programming. With this, it's going to be a little bit different. You're going to have to learn a bit more of an overhead in learning. Non-uniform memory access times. This is the biggie with message passing, is that you are not necessarily going to get the same reaction time communicating between nodes every time, and you have to be aware of that. You have to plan for it. The access times will be affected by the network. Could be other people using the network. You could be using it on Ethernet, depending on what you're doing. You have to be aware of the fact that networks do fail. Maybe a remote node fails. For anyone who's familiar with Hadoop, this is more or less how Hadoop is going to act, and it has taken into account a lot of the failures that can happen for you, which is not the miracle of Hadoop, but what it does. So, challenges. What are some of the things we're going to have to deal with? This is going to be a bit more of the nitty-gritty of parallel programming. But some of the things we have to worry about is non-determinism. When I'm talking about non-determinism, that means you may run a program twice with the exact same input and get two different outputs. And that's because when you're running multiple processes, things are going to happen at different times. And if the order matters, you're going to get a different output. So often you have to account for it to make your program deterministic. Or if you're using a non-deterministic program, you may just get lost in the fluff. Communication. The last couple of slides I was talking about the difference between shared memory and message passing. You have to be aware of the type of communication that's taking place and how to implement it and what kind of effects it's going to have on your program. Now, synchronization, which would be the synchronization between threads and talking about a little bit of how you're going to protect variables and such. This is how you're going to coordinate threads, how you're going to make things work. And finally, data task partitioning. That is more the design. How are you going to design your parallel program And I will get into that after I deal with the first three challenges. And I'm going to talk about metrics. So the data task partitioning is going to be more, that's what we're talking about. We're actually talking about design patterns. So first, non-determinism, race conditions. Race condition is probably your most common type of problem that's going to destroy the deterministic nature of your program. So say we have this, and it means that things can happen out of order. It's basically what we're saying. Because the processes are executing the same statements or different statements at the same time, you don't know how they're going to get interpreted. So we're going to look at this example where we're going to say transfer from some account to some account an amount of money. Now you may write it as from your account is equal to the from the account minus the amount. And then you'll say to is equal to 2 plus amount. And that looks to you like two statements. In reality, the computer is going to look at it as more than two statements. Often, 3 or more statements, depending exactly how it's going to be coded in assembler. Now, each one of these could be atomic or could not. And when I say atomic, that term means uninterruptible. It means that access to memory or this operation is not going to be interrupted. And often, one line of code will consist of dozens of atomic operations. So at any time, something could be inserted between there or could happen at the same time. So to look at this transfer, in reality what's going on is the from value is being assigned to some temporary variable, probably a register on the CPU. An amount is being subtracted from that temporary variable, and then it's being reassigned back to from. And then the same thing is happening for 2. So in this example, we're going to have 6 operations, which for all intents and purposes we will consider atomic. So say my account starts with $500, and I've got 2 clerks. 2 clerks want to transfer money. One from some account B into my account, $200, and another one's going to transfer from my account to some other account, $50. Now you're going to say to yourself, if you think about this logically, what's going to happen? What should be the outcome? Well, someone's adding $200, so I get $700, and they're taking away $50. I should have $650. Or that could happen. You think, oh, well, it could happen in the other direction. You could take away $50 first and end up with $450. Add 200, have $650. In either case, I should have $650 in my account. However, that's not the case. Because we're talking about these smaller operations which can be interrupted or interweaved, things can go quite awry. So let's look at this. We'll break it down step by step. Keep in mind that these transfers are occurring at the same time. So for clerk A to transfer from another account into my account $200, the first thing it does is it assigns the temp 300. Temp is equal to $300. Okay, with $300 being the amount. That should be 500. The amount that is current. Oh, no, sorry, 300. That's in B account. And then clerk B assigns the temp, their temp variable, 500, the amount that's in my account. Temp minus equals amount, $200, has no problem. So their temporary variable now has 100. At the same time, their temp minus 50 will leave 450 in clerk B. So you'll notice there that we go down to clerk A is going to say, okay, clerk A is going to assign $100 to B. Right, that's what's left. It's been assigned. That's from the first part. Clerk B experiences some sort of delay. For some reason or another, we don't know. They went to get a coffee. The CPU stalls out. Something happens that it has stopped executing that at that point. Well, clerk A has no problem. It continues executing. And now it's doing the other part of the transfer. It assigns my $500 to a temp variable. Remember, we haven't written back anywhere on clerk B saying that 450 is there. It will add the $200 to the temp, $700, and assign $700 back to my account. Well, that seems right. You have 500, you add 200. But remember, what happened up here was the temp was assigned on the second step. 450 was assigned to it. The next step is to assign it back to my account. So clerk A has assigned back 700. Now we're assigning back the 450. So this means that the $200 that was just transferred from one clerk has been ignored by clerk B. And that is because it was in a temporary variable on a register on the CPU. And you got what is called a race condition. A race meaning whoever gets there first, it's going to matter on the outcome. So you have a non-deterministic program. So you have to be aware of this. These are what we'll call critical code, critical sections. And these are what we're going to be worrying about when it comes to mutual exclusion or mutexes. So what will happen is, so in this chart here, it's basically we have two processes. They're going along through time, and they get to what we call a critical section. And we are going to surround that critical section with what we call a mutual exclusion lock, or a mutex. Sometimes a semaphore. There's a lot of versions of these. The basic one is a mutex. So as time progresses, both are running at the same time. They get into a critical section, only one thread can be executing at a time. And this will prevent things like race conditions. And then once they exit the critical section, they can continue executing. To take a look in a bit more detail, so say we have some code. Now we're going to say lock and release. What happens is, when you call a lock, only one section of code, or one thread, or one process, one CPU, whatever granularity you want, can work on that code at a time. So they'll both do stuff before. Lock, only one will work on the critical code section. Release, and do stuff after. Now this is key almost to everything. Everything else is going to be built on top of mutexes. All of your communication. There's different levels of mutexes. You can get mutexes for communication. You can get mutexes for symmetrical multiprocessing, etc. But the general idea is here. So we'll take a look at thread 1, do stuff before at the same time that thread 2 does stuff before. They both call lock. Now only one can get the lock. Only one thread can have a lock at the same time. The other thread will be considered to be waiting on the lock. Thread 1, therefore, gets the lock and enters critical code. It then releases the lock and does stuff after. Then thread 2 will perform the critical code, releases the lock, and then continue to do stuff. Now that's the basic idea of a mutual exclusion lock, or a mutex. Keep in mind that there's other things. There's things called trilocks, which means lock, do the critical code. If you can't get the lock, do something else. There's semaphores, which means that a certain number of threads are allowed within the critical code section at a time, often used for resource control, to say you have only so many file locks you're allowed to give. There is also a barrier point. And a barrier point is similar to a critical code section, except to say that we're all going to stop and wait at the end or the beginning of the critical code before we continue. So that's just to say that these examples are not the be-all and end-all, and there are definitely more. Now, once we have introduced mutexes, we get into this problem of synchronization. And the big dreaded word of synchronization is deadlocks. Now, the first rule of a deadlock is a deadlock can only occur if you have two mutexes working at once. When that happens is, a deadlock will happen when one mutex or one thread is trying to get a mutex that another thread holds while holding another mutex that that thread is trying to get. Kind of tongue twisty at first, but let's take a look at this transfer. So we've now fixed the transfer method so that we now have two mutexes in there. We will synchronize on the from account, which means it's a lock. We will synchronize on the to account, which means it's locked. We will then enter our critical code section, our from and to, and then release the locks. And we release them in the order in which we get them. And that seems good, because if you release them in the order you get them, nobody can hold the lock at the same time that somebody else is looking for it. So if, in theory, thread A, if they're looking to synchronize on from, will get it before it attempts to lock to. So nobody can lock to without first locking from. And this at first looks like a good way to protect against deadlocks, and it is one thing you'll do. However, you'll note we made a critical error down here when thread 1 calls transfer A to B and thread 2 calls transfer B to A. What will happen is this thread 1 will get the sync from, at the same time, or possibly at the same time, that thread 2 is syncing on its from, which is its 2. So you can see how they get locked backwards. That means that they're both going to be attempting to get the same mutex at the same time. They're going to be sitting between the two, and the program will not progress. There are numerous fixes to this out there. Feel free to look them up. The one would say to sort them. You can sort which thread is from and to in the order of the mutexes. I want you to be aware of the fact that deadlocks exist, and you have to be careful. And we are going to move on to performance metrics. So kind of a shift in what we're talking about here from some of the more mechanics to what we're going to talk about more reporting on what we find. So metrics, what I mean by metrics is measures of your parallel program. And there are 4 basic measures on how you report on the performance of a parallel program. The first thing is you always want to include a serial runtime. Without comparing something to a serial runtime, we really don't get any measure of what's going on, no comparison. We'll call that T1, stands for time 1. Parallel runtime at n processes, T at n, which would be how much time it takes to run the same program, the same inputs, for n processes, n threads, and whatever, n threads of execution. Speed up time. Now this is the times faster that your T of n will run over T of 1. That's simply S of n, for speed up, is equal to time at 1 serial runtime, or sequential runtime, over parallel runtime. And then there's another metric called efficiency. Now at first it may seem that efficiency and speed up are basically saying the same thing. And they kind of are, but they graph differently. And the reason they graph differently, or the reason I'm showing you this, is because one's a bit more intuitive to show you how well a program is actually performing. So we will start with the naive chart, which you include, for the record, you include all 3 charts that the reader choose. But what this chart shows is runtime. And we can see this program, this hypothetical program we've got, runs at 10 seconds for 1 thread, slightly more than 5, and so on. It looks like a nice little curve, right? Showing you how long each process or the program takes to run, given the number of processes you've provided to it. However, there's a kind of a misleading thing here, and we can check it when we look at speed up. Now, remembering speed up is sequential over parallel for any given n. So at 1 core, it will be the same, because it's just T of 1 over T of 1. And now note that our metric is now times faster instead of some arbitrary measure, seconds or minutes or whatever. It's just times faster. And you can kind of see in the light blue line there is what we're actually achieving. And then the dark green line is optimal. And what I mean by optimal is you're not experiencing any slowdown. You're not experiencing any performance hit. Not a lot of communication, not a lot of context switching, or the kinds of things that will harm the performance of a parallel program, which almost never occurs. So we can see, whereas before it looked decent, a nice little curve, it's cut in half each time. Now you can see, compared to the actual, it's not necessarily what we'd want to get. Now for efficiency, this is normalized. What will happen with efficiency is we've got a metric from 0 to 1. Now this is not to imply that you can't get more than 1, but if you see more than 1, you're weary. It might be a reporting issue. Superscalar or better than 1 efficiency is something, the holy grail. But in this case, it goes down as you would expect a program to. As you increase the number of processes, the efficiency or the amount of speed up you get goes down. If this was no overhead, we would have a straight line along the number 1 line here, implying perfect efficiency. However, you'll typically get it going down. So you can see as we increase the number of processes, our program, while running faster, is not running as much faster as we'd like. Now these charts are always good if you're going to do a measure of your program and you want to report how well it parallelizes, how well it scales, charts like this are the kind of thing you're going to want to introduce. And the reason for that, and I apologize, is a bit of math, is Amdahl's law. Now, Amdahl's law is basically explaining / predicting what kind of efficiency or what kind of speed up you get. He calls it speed up and latency. It's the same thing as speed up. So we're going to start with the percentage of the program that can be parallelized, P. So there are going to be some parts of the program, typically at the start and at the beginning, or any time there's a critical code section that isn't running in parallel. And you take that, we'll say P. The percentage of the program which can be parallelized, is P. The percentage of the program which is serial only is 1 minus P. So obviously the serial part is just the remaining from the parallel part. So we can say that serial runtime, T of 1, is 1 minus P, which is the amount of serial runtime times the actual runtime, plus the percentage of parallel runtime times the actual runtime. And that's just saying that serial runtime is serial runtime. The next part of that, where we say theoretical parallel runtime, T of n, we're going to take the serial runtime equation, where we take the percentage of the program which is serial only times the serial runtime, plus the amount of program which can be parallelized times the serial runtime divided by the number of cores you have. So this is where we're getting our improvement by parallelizing. And you'll note that on the first part of this equation doesn't change for the number of cores or number of processes we're running. The second part does. And that shows that the first part here is our overhead. That's the critical code sections, or the startup, or the rundown, or the teardown for running our program. So we're going to reorganize this a little bit, and they show it as T of n over T of 1 is equal to the amount of the program which can be serial only, and plus the amount of the program which can be parallelized divided by the number of cores, which you may recognize before as our speed up. So what is going on with Amdahl's law is this is a way of predicting. You can plug in what you get on a sequential or a serial run, and you can plug in what you get on a parallel run, and you can predict or give a metric to how much overhead your program has, how much parallel runtime only. Now note, this also shows that there is a portion of your program which, no matter how many cores or how much parallelism you throw at it, there's a portion of your program which is not going to get any faster. And that's what Amdahl's law states. It states that the minimum execution time of a parallel program is dictated by the execution time of the serial portion of that program. So you can only get so fast. What are some of the things that are going to cause serial execution in a parallel program? Disk I/O, writing to the disk, writing in and out. So when you make your program, think about where your disk I/O is. Don't do it all over the place. Maybe do it at the beginning. Maybe save some of it in memory. Write it out at the end. Interprocess communication. A lot of interprocess communications involve mutexes, or some sort of mutex, usually at least between two of the processes, sometimes between all of them. Critical code segments, things where race conditions can occur that you don't want. That's going to cause a serial portion of your program. Lock overhead. Every time you use a mutex, there's actually quite a bit of overhead in locking it and releasing the lock. There's also a lot of context switching is a similar overhead. When I say context switch, that means starting up, firing up a thread, firing up a process, tearing it down, the kind of things the operating system has to deal with, it's going to deal with in serial. And latency. Latency P can change according to the number of processes. So you can actually get more overhead depending on the number of processes you run. And that goes back to our architecture. If the number of processes you're running doesn't get off the chip, say you're using a multi-threaded program, it's going to be less overhead than if you've got 2 chips and they have to share across the bus, which is going to be less overhead than if you have to have message passing, and so on and so forth. So you want to try and keep all of this stuff in one spot to reduce the serial portion of your program. All right, so now that the lexicography, I guess, Now that we have a bit of a language for talking about parallel programs, we're going to switch gears again and talk about patterns. Now I am going to talk about 5 patterns. The master worker, previously known as the master slave, sometimes called the farmer worker. Multi-walk, pipeline, hybrid, which means a mix of others and what you have to consider, and loop parallelism. Now, as a caveat, before I get into design patterns, they're all basically the same thing, but with different ways of looking at it. A lot of programs will fit into more than one design pattern. You want to choose the one that just makes the most sense to you, the most sense to the person reading it, and the best way to get your idea across. Which one is appropriate. So you can pigeonhole your program into any of them. And that's true of all design patterns, not just parallel design patterns. And there are going to be some times that you break the pattern a little bit, and that would be, say, we're using this pattern, here's how we don't use this pattern. And that's just a caveat, because there's always some sort of academic discussion over which design patterns you want to use and which you don't. Take what you want, throw out what you don't want. That's what it comes down to. So we're going to start with master worker. This is a very popular one and has been used for quite some time. And what is going on is we have a master process, and it means we're running in serial, we're running sequentially. They will split up the tasks to perform computation to the workers. Here I've got 3 workers. It can be as many workers as you want, which will then stop working in parallel and go back to the master, who will perform some computation. Now, note here at the beginning and at the end is where the communication is going to take place. Because in a master worker scenario, all communication is between the master and the worker. And that means we've isolated the communication, therefore reducing the sequential part of our program. We don't have the workers communicate with each other in this model, and that will prevent certain critical sections from occurring. You want each worker working on one task. This is good for things that can be divided up into tasks. You can take some sort of data, they're all doing typically the same task, and so you divide the data up, have it all done, put it back. Anybody who is familiar with a genetic algorithm in which you'll just be doing the same task over and over again, this is a good model for that, because you can farm out the computationally intensive part to the workers. Now, when we see the master, if you're thinking about it in a thread way, you go, oh, this is 4 threads. Well, it is 4 processes, but you're not necessarily going to be wasting CPU power. So if this is a 4 or a 3 CPU machine, the master is going to sleep in one of the 3 core machine, I suppose. And one of the workers will take over that core. And that's to say that the master can either wait, block, or it can perform computation. Most threading programs and most message passing will take care of this for you. You don't have to it'll just sleep the master. Scalability. This is not a inherently small pattern. Hadoop, the famous big data pattern, is just master worker on a large scale. MapReduce. So MapReduce is just master work on a large scale. Well, what you're doing is the master is mapping, the workers are then doing the work, and then the master reduces again. Same thing, different scale. Very scalable pattern. Simple to code. Very simple to put together in that you're doing all of the division of labor at one point. It's temporally well suited. No interworker communication. So the workers don't communicate with each other. I mentioned that. However, single point of failure, and that's not a good thing. What this is saying, and this is particularly when you talk about Hadoop, and they talk about its redundancy. Well, there's still the one node that is dividing up the work to the different, I think it's multi-level master worker if you want to think about it that way. But if the master in this case gets a problem, or there's a problem with that communication, it fails. If wherever your master is running, the whole thing's going to fail. If you've coded it incorrectly, whatever your causes your failure, it's not necessarily hardware. You're going to have a single point of failure. It's not fairly fragile system, as opposed to multi-walk, single program, multiple data. Now this is almost serial farming. And the reason it's not serial farming is because of this thing in the middle, communication. Communication or critical code section or barrier. And what the model this time is doing is each process is working independently from the others and will then communicate with the other processes as it sees fit. And whenever that communication takes place, then you're risking sequential execution in a parallel program. The communication between processes, not necessarily all at once. One process could talk to another while others continue. When they all stop like this, that's considered a barrier point. That is where they all stop, they all communicate, and then they all continue. This is not suited for a large variation in process runtime. Whereas in the master worker version, you can divvy out work. The master might be working in a thread on its own, give it a round robin, and it's appropriate for possibly different sizes of work. Because if the amount of work here at the beginning varies a lot, the other ones that are waiting on the barrier have to wait until all processes are done before continuing. So if you've got different amounts of work on the processes, not very suited. Prone to communication delays. That means while the communication is taking place, everything might have to stop, in this case, because of the barrier. If you're only communicating between two threads, maybe another thread wants to communicate with the thread that's communicating. So it's prone to a bit more communication delay than the master worker, where all the communication is happening at one point. But of course, this is more versatile. It's more expandable in your design. Pipeline. Now, the pipeline gets its own mention in that it's a different way of thinking about the multi-walk. What's happening here is you can think about it as an assembly line, and that how an assembly line in a factory works, where you start, say you want to put something together, the first process. Well, it doesn't take very long, so we're going to assign it one process. It will then feed its information into a queue from which the next processes take out of. So the reason there's 3 on the second step is because possibly this is more computationally intensive, and it will have to pull it out. So you can see that it's dividing up the work. And that puts the work back together into another queue where the third step has 2 processes. And the point here is each step is meant to be independent of each other, and thus have different runtimes in individual steps, different communication models, and is kind of suited to that process in a stepwise manner. Now, it's a queue-driven model, and because of that, so each process is individually pulling from one queue and pushing into another queue. It's prone to starvation. It's prone to not having enough work to do in a certain process. And that would be if one process isn't performing well enough or fast enough to fill the queue, the next process will starve and it'll chain down the line. This is typically fixed by having variable sized process pools. We'll move processes around to different steps to speed up or slow down different parts. This is similar, and there's different ways of explaining pipelines. Instruction pipeline on the CPU level is one, if you're familiar with that. But there's also the graphics pipeline. If you've ever done graphics programming, OpenGL or such, when you run things through shaders, you'll load up all your data, process it all, and then select the next step. Load up all the data, process it all. It won't necessarily process all at once because it'll be fed into a queue to go through the microcores. And that's a similar pipeline situation. But in that case, you're stopping and you're reassigning all the microcores to a different process, if you're familiar with that. And this kind of stop and go thing is where we're going to go into loop parallelism. Loops are great for parallelism in that they're just obvious. You go say, oh, we're going to do something 1,000 times in a loop. Let's split that up. It's like loop unrolling. So what we're doing here is we're starting on one process. When it gets to a loop, we split up the processes, thread it, which will then repeat until it's done, and then continue in a sequential manner. Some of the things you have to worry about concerning loop parallelism is data independence between iterations of the loop. So it's not necessarily always suited for all loops. Some loops in which one iteration of the loop, what happens on one iteration of the loop matters for the next iteration of the loop, isn't necessarily going to work. However, when it does, when it is appropriate, it is very easy to implement. Some languages do it automatically for you now. This is the kind of thing that can be just found. Susceptible to race conditions from mutex locks on critical code sections. I don't like the way I wrote that, but what I'm trying to get at is it's susceptible if you didn't do it properly or didn't properly do the loop, like divide up or choose the loop, then race conditions can happen. That means that there's no loop independence. If you have a mutex in between one of the loop iterations, it will lock down all of your iterations and cause a bit of a problem. So you have to make sure that those aren't there. In this case, we are going to use, and we're going to move on to, what we call a hybrid pattern. Now, what you'll do is hybrid patterns, known as nested patterns or asynchronous patterns, is a composition of patterns. And it will result a number of subpatterns or macro patterns. But what you do is you identify the input and the output of a pattern, and you can swap them in and out. So you'll say we're going to have a loop unrolling or a loop parallelism, but inside each loop we're going to have a master slave, or we're going to have some other model. What you have to worry about here, and this is what I'm trying to get at here, is you can kind of mix and match your models. You can mix and match what you're doing and try and describe them as a multi-walk with master slaves inside, with loop unrolling inside, etc. But your major concern there, like I said, is as you switch these things out, is the input-output dependencies. And that means that you're going to, this is back to old Hadoop with your map reduce, is that your input of one has to match the output of the other. And you have to be particularly careful with that. But this is more of a last slide mention, because now the presentation is over.